So the next section we're going to look at here is optical laser testing. And we're going to focus kind of on three methods for this one. Oops, there we go. And those three methods, first we're going to look at holography, which you can see it shares a word with hologram, shearography, and then the third one we're going to look at is profilometry. So holographic testing, known by its full name as holographic interferometry, is where we use holographic technology to map the surface of a part. And what this is, it is a method, kind of like acoustic emission, where we have to stress the part. And so we're going to compare, we're going to look at a surface when it's not stressed, and then we're going to put some kind of a stressor on the surface, and we're going to look at it again, we're going to image it again to see how it appears under stress. And what happens is if you have areas of discontinuity or flaws or weak areas that are weak, or that maybe like in a skin, an aircraft skin where you have an oil canning effect going on, those areas are going to show up in differences in how the material deforms when that stress is applied. Now, when I say deform, I don't mean like deform to the point where something looks visibly damaged, but just, you know, we know that, for instance, when you pressurize a fuselage, the fuselage expands a little bit, you know, very, very tiny. Not enough we can see it with the naked eye, but a holographic testing system would be able to do that amount of expansion. And if you have an area where the skin has weakened, just like if you have an area, anyone ever like blow up a balloon, you get that little bulb spot that sticks out where the rubber is weaker than the rest of the balloon, right? You'll get the same thing happening with, or if you've like blown up a balloon, it gets all stretched out, then you blow it up again, it looks funky. You'll get the same thing happening with things like aluminum skin and other materials that are subject to stresses in their plastic range. Okay, or sorry, their elastic range, the elastic range where they tend to return back to normal size. Sorry, elastic deformation range, not plastic. So there's different ways we can stress the part. We can do it mechanically. Mechanically could include things like pressurizing the aircraft. That's a form of mechanical stress. Using pressure, so the pressure creates a mechanical stress. We can heat and cool, heating and cooling, changing temperature. You can also use things like vibration. You can put a part under a vacuum, which again induces a mechanical stress in it. And it's going to cause that surface deformation, and then we're going to be able to pick that up and make an analysis of underlying structural condition, whether it's the structural condition of, say, the material itself or the underlying structure that supports that material. So the theory in the process here relies on interference patterns that are created in light due to the light wave phase change, okay? So we know that light, right, has that, going back to physics 101, light has particle wave duality. Sometimes it acts like a particle, sometimes it acts like a wave. But it is when it's in a wave, you have a phase structure to it, right? And light, normal light, what we have bouncing around the room, you know, if you think about it in wave kind of format, right? Some of the waves are going up and down, right? And some of the waves are going side to side, and some of the waves are going at this 45, and some of the waves are going up, you know, they're at all different angles, right? So normal light is not in phase. It has all kinds of, you know, it's at every direction. But if we use something to polarize that light, if we use a laser light is light, it's run through a polarizing filter, so all the waves are in the same direction or in the same plane as one another. And when they're together, it creates light, they constructively interfere. And if they become out of phase, if you get two light waves that are parallel, but are out of phase, they will interfere with each other. They'll create destructive interference, and you'll get a dark spot in that area. And so what happens is we take our in holographic testing, we look at, you know, so normal photography, we're just looking at the light intensity. That's how your eyes are working right now. All you're really seeing is the light intensity. We don't see phase as humans. we don't know which direction the light wave hitting my eye. I don't know if it's going up and down or left or right or at an angle or whatever. Now, sometimes, probably many of you have worn like polarized sunglasses to if you're around water. Those block light waves that tend to reflect from below. So light that reflects off the ground has a certain wave orientation. And so polarizing lenses are designed to block that. This is kind of taking polarizing lenses on steroids, running all the light being projected through them rather than filtering it when it comes in. And so the light coming out of that lens is all going to be in phase. And that's what laser light is. And then for holography, though, when we take our images of it, we're not only going to look at light intensity, but we're going to be looking at what the resulting phase is. We know what the starting phase was. We're going to look at what stayed in phase, what phase changed, and be able to tell. And so this was early on, what we can see it as was what's called Young's double slit experiment. So I got a couple of videos that just show the interaction, what you see when light is in phase and what you see with destructive and constructive interference.